So this week we have to go over the measures of dispersion. Up until now, we've been doing things that sort of intrinsically come along. You have information, you have raw data, and you tend to want to organize that data in some fashion. And we tend to do it by seeing how things are alike, right? How they cluster, like we did with central tendencies, mean, median, mode. See, how are these things alike? What's the relationship? How closely do they cluster? And even if you think back to frequency distributions, that sort of has the same pattern. How many of these do we have versus how many of these do we have? And what percentage of our total are these things? With measures of dispersion, it's not the go-to approach that we like to take with numbers. So for some of us, this gets a little bit tricky. This video, we're going to go through the 4 basic measures of dispersion: range, interquartile range, variance, and standard deviation. And we'll go through them step by step so that you can do the calculations. Now, as far as what we do with standard deviation and variance, well, we'll worry about that in a different video. First, let's get the calculations down, and then in a later video, we'll talk about position and what to do with those things. So, measures of dispersion. So the first of the measures of dispersion that we have to speak of is the range. The definition of the range is the difference between the largest and the smallest values in a data set. So let's come up with a data set that we'll put up here. And again, we're going to keep the numbers as small as possible, just so we can get the concept. So let's say it's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So that's our data. Now, if this is a population, of course, we would know that would be a capital N equaling 10. If it's a sample, it would be a lowercase n equaling 10. But we know we have an n of 10. Now, if you were to ask a person, just walk up to anybody and say, what's the range of this data? They would probably tell you 1 through 10, or 1 to 10. And although it's not entirely wrong, it's not exactly how we're going to use the word range in a statistics class. What they're telling you really, when they say 1 to 10, is they're telling you the lower boundary, and they're telling you the upper boundary, which is part of how we're going to calculate the range. But the range, as we said before, range, I'm going to put it as a capital R, equaling the highest value minus the lowest value. So there has to be a little bit of math done with this. So if we're looking at this data set, let's say we take the range, again, range equaling, well, we know the highest value here is 10. So it's going to be 10 minus, and we know the lowest value here by looking at it is a 1. So 10 minus 1, we have a range of 9. So the range of this data set that we're looking at, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the range of that data set is 9. Now, we want to be careful with the range, because although it does give us some information, it doesn't give us much. And one of the things it's doing is it's ignoring everything here in the middle. Right? It's only concerned with the ends, with the extreme values, the low and the highest. And if either of these become either the lowest or the highest value becomes too extreme, it could misrepresent things. So let's look at another data set. So for this new data set, I'm going to change the ink color. Here's the new data set. 1, 1, 1, 1, 1, 1, 1, 1, 1, 10. So this is the new set of data. With this data set, we also have, if it's a population, an n equaling 10. If it's a sample, a lowercase n equaling 10. But again, n of 10. Now, if we're going to calculate the range on this, the formula remains the same, right? So we have range equaling the highest value minus the lowest value. So the range equaling the highest value in this case is 10. So we have that. Minus, and the lowest value in this case is 1. Same as the previous set. And the range in that case would equal a 9. That's a 9, believe it or not. Now, measures of dispersion tell us how the data disperses, how it varies. What's the difference amongst the datum themselves? And if we look at the first data set here with a range of 9, well, there's a bit of variability. If we look at this here, though, this data set is basically the same with the exception of this outlier here, an extreme value. So the range, again, the highest value minus the lowest value, this is impacted by outliers or extreme values, similar to in our measures of central tendency when we spoke of the mean. The mean is also impacted by outliers or extreme values. And the other problem with the range is that it ignores all of this stuff here in the middle. It's ignored, right? Because it's only concerned with the high end and the low end of things. So how do we then take a look at a different way to do a range that would factor in these middle values? So what do we do? What type of range does not ignore the middle values? Well, for doing that, we're going to need the interquartile range. And this type of range doesn't ignore middle values. As the name suggests, you're dividing the data into 4 parts. So let's put that data set that we had up before. Let me change the color again. Probably should put it as black because anyway, my cursor looks like it's going to be red. Now here's the data we were dealing with before, right? We had 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And we know that was an n of 10, right? Let's put that n equaling 10. And we know we had a range before of 9. So now, let's take a look at the interquartile range, and let's calculate that. Now, in doing this, in some textbooks, and depending upon who you're speaking to, sometimes interquartile range gets lumped in with the central tendencies because it does have that sort of a quality to it as well. And it does involve understanding the central tendencies to divide the data into 4 parts. But let's go over it. First, we want to find Q2, which is the median of the entire data set. So you guys know how to find the median, the depth of median, which in this case, we would say 1, 2, we got an n of 10. So if we're looking for the depth of median, it would be 10 plus 1 divided by 2, which we would find would put Q2, I'm going to change the color again, make this a little bit easier to see, hopefully. Q2 would be right here. So Q2, and let's write it over here just so we can keep track. Q2 would equal 5.5. And remember, if we're looking for this, go back to the central tendencies video to see how that gets calculated out in finding the median. So we found Q2. The next part, we want to find Q1, which is the median of the data set below Q2. And with Q2, we've divided the data into 2 parts, right? We divided it in half. So we want to go to the median of the data set below Q2. So below, in the lower ranked, we're talking about, this area down here is below. So we have 5, which is nice and easy because it's an odd number, which would put Q1 right here. So Q1 equals 3. We need one more cut to divide this into quarters. So we need Q3, which is the median of the data above Q2. So now we're looking at this side up over here. So we know there's 5 over there. Okay, so we can have Q3 is right here. We found our Q3, and Q3 equals 8. So we divided it now into 4 parts. And we have the values of Q2, Q1, and Q3. So now we have to calculate the interquartile range, which is abbreviated as IQR, which is interquartile range equals Q3 minus Q1. So if we're going to put this in here, let's say we have our IQR equaling, well, it's Q3. And Q3 we know over here is 8. So 8 minus Q1, which is 3. So we have an interquartile range equaling 5. And we had a range before of 9. So this is not ignoring the middle values. Let's take a look now at the other data that we were working with before, which was all ones except for an extreme value of 10. Right? There was very little diversity in the data set. So let's put that up here now. So we have 1, 2, 3 ones, a fourth, a fifth, a sixth, a seventh, 8, 9, and we have this one here, 10. So again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have an n of 10, right? Which we assessed that before too, right? An n of 10. And with the range in this, we also had a range that equaled 9, which was the same as the data above. Let me make that 9 look a little nicer. That didn't help much, did it? So the middle values are getting ignored here. Now we're going to apply the IQR. We're going to do an interquartile range to see if that tells us something different about this data set and the dispersion or the difference among the data. So again, we got to find, first step, find Q2, which is the median of the entire data set. So again, this is going to be, we have an n of 10, 10 plus 1 divided by 2. That should put us right here. Little arrow there, which would be our Q2. Now again, finding this, refer back to central tendencies. But we know Q2 at this point equals 1. Now we got to find Q1, median of the data below Q2. So that's going to be here. So we got our Q1, and Q1 is also 1. So Q1 equals 1. So now we got to find the data, Q3, which is the median of the data set above Q2, which would put us here. Q3, which divides the data into 4 parts, and Q3 is also 1. Now let's finish it up by doing the calculation of the IQR. So the interquartile range equals Q3 minus Q1. So this was going to equals 1 minus 1. So you have an interquartile range equaling 0. So what does that tell us? Well, it tells us what we can assess just by looking at the data, because it's a small data set. All of this here, there is no dispersion. There is no spread, no variance here. It's all the same. We have a high value here, which is what's giving us the range of a 9, but an interquartile range of 0. So you see something along these lines, you say, okay, you have an interquartile range of 0 and a range of 9 with an n of 10. We have an extreme value in there. It lets you know what the middle values look like, what the dispersion looks like within the middle. It's not ignoring the middles. And that's the interquartile range. The third measure of dispersion that we have to talk about is variance. Variance is the mean of all squared deviation scores. So you hear in the definition that it's a mean. And the formula of a mean, where you add up a whole bunch of something and divide it by something else, is a reoccurring theme in statistics. Now variance, again, the mean of all squared deviation scores. The formula is going to vary from population to sample. There's slight differences. We're going to start with the population. So what we're looking at here is the symbol, lowercase sigma squared. That's the symbol of the population variance. The formula here in the numerator, this is referred to as the sum of squares. This is the x's minus the mu's squared, and it's all added up, right? You have capital sigma summation of the x's minus mu's squared divided by n. So again, when you see this formula, when you come down to the end of it, let's say, for example, you have, I don't know, let's say variance equals 220. Let's say that's what you have. Variance equals 220. You don't square it from there. The formula itself takes care of the square. So you don't have to worry about squaring. And once you see lowercase sigma square, you'll know that that's what you're dealing with here. Let's just erase those. Let's get that out of the way. So let's take a look at doing this particular formula. Let's have our data set. We'll put the data up here, and we'll have it, let's say, 10, 15, 20, 25, that's a 5, let's fix that a little bit, and 30. So that's our data, that's the raw data. Now looking at this here, again, going back to this formula, you need a few things. One, you need to know what's n. Okay, let's take a look. 1, 2, 3, 4, 5. So you have an n of 5. So n is population, so capital N equals 5. What else do we need to know? Well, in looking at this, we're going to need to know mu. So mu, which is the mean of the population, we need to calculate that. So pause the video, calculate that, and then we will resume. And having done that calculation, you have probably discovered that the mu, or the mean, is 20. So now let's finish the calculation. We have the two things that we know we can get just by previous videos and looking at it. Now we have to calculate the sum of squares, which is the summation of the x's minus the mu, or minus their mean, squared. Easy way to organize this, and I would recommend this, is doing it in a chart format. Now this can get rather lengthy, but you'll see how the organization keeps it a little bit easier to follow. You're going to have one column for your x values. So that'll be the column for your x values. And what are our x values? Well, our x values are the data set that we're looking at here. These things over here. So we have our 10, we have a 15, we have a 20, we have a 25, and we have a 30. So those are our x's in the column. The second part of the column is going to be this part over here of the formula. So we have, keep parentheses in there, we're going to have the x's minus their mean Let's take a look at that. X is minus the mean. So we know we have a mean of 20. First x is 10. 10 minus 20 would give us a negative 10. 15 minus 20 will give us a negative 5. 20 minus 20 gives us a 0. 25 minus 20 gives us a 5. And 30 minus 20 gives us a 10. So your second column is now done. Now as we look at the formula here, these things have to get squared next. So let's set up our third column. And in the third column, this will be x minus mu squared. This is where the squaring of it enters into this. So let me change the color back to red. Let's do that. So negative 10 squared gives us 100. Negative 5 squared is 25. 0 squared, well, that's still 0. 5 squared is 25. And 10 squared gives us 100. Now the next step is you're going to have to, again, following along, you're going to have to add this up. So the summation of this. So let's put the summation symbol here, and we add this all up. That'll turn to 250. 250 would be the summation. So in the formula, if we're writing the formula out here, let's say we have square. So we have our variance of a population equals the sum of squares, which we now know is 250, divided by, according to the formula, n, which is 5. That would give us the variance equaling 50. So if we put our variance score up in here, we can put our sum of squares, which, let's say we have sum of squares, SS, is 250, and the variance equaling 50. All right, I'm just going to erase some of this stuff so I can bring up another part. We were talking about how the formulas will be a little bit different for samples versus populations. So if we were to take a look now at a sample, in fact, you know what? Before we go on to that, I'm going to erase the mess around here too. Let's clean some of this stuff up, right? Let's get rid of some of this, because you may want to look at that in a neater sort of fashion, especially now that we're pulling up a sample. Let's see what the differences look like. Okay, for starters, the symbol is different. Instead of what we have here is a lowercase sigma, here we have an S. The square is the same. Into the formula itself, it's a sample. So where we have in the sum of squares formula here, the sum of squares, which is here, instead of mu here, it's x bar because it's a sample. And a big difference falls into this here. N minus 1. N minus 1 is a formula referred to as degrees of freedom. And degrees of freedom basically tells us how much the sample is allowed to vary. We'll talk more about degrees of freedom in a different video, but the basic idea comes down to this, is that samples are not perfect, and there's going to be some variability within there. How much are we allowing the variability to occur? And as we'll see later on when we talk about t-test, degrees of freedom helps to straighten the curve out when we subtract out 1 from our sample. So n minus 1 is what we call degrees of freedom. The formulas are, these two formulas, population and sample, are mathematically almost identical, right? You have your sum of squares on the top here, you have your sum of squares here. The only real difference is how the mean is indicated. Is it indicated by mu or is it indicated by x bar? And then we have, instead of dividing things by n, we divide it by n minus 1 degrees of freedom. The rest, this stuff all over here, right? This stuff all here, this all stays the same. You don't have to worry about redoing this as far as whether or not it's, if you've done it as a population, now you want to try it as a sample. None of the stuff in this chart over here, none of this stuff is going to be different. If you're just calculating out a sample, this chart works the same way. Nothing changes. What does change, and let's say we're going to do this, I'm going to change the ink color. Let's make it green this time to indicate our sample. So let's say now we're doing a sample. Well, n, and we're still working, again, we are, if I can find my cursor, there it is, we're still working with this data here. Okay, so this is still the data we're working with. We have an n of 5. It's lowercase because it's a sample this time. We have a mean. The mean is going to be x bar, right? So x bar, and the mean is 20. So yeah, you would change this up here if we're doing this as a sample, right? We would change this. We would change that to x bar. And we would also make that same change over here. We would also change that then to an x bar as well. Let me just get the color up, and there it is. So the chart would look a little different as far as that goes. So x bar would still equal 20. The sum of squares, the calculation is going to be the same. So the sum of squares, which we'll put here is S, that's still going to equal 250. But now we have to add degrees of freedom, which we'll notate by df, degrees of freedom, which is n minus 1. So n, which is 5, minus 1 would give us degrees of freedom of 4. And that would change the equation here. So where before we did 250 divided by 5, now for s squared is going to equal 250 divided by 4, which then would give us s squared equaling 62.5. So, and then our variance would equal 62.5. Now, when you write these things up, I would do my best to keep everything aligned as neatly as you can in the columns, right? You want to try to keep this as neat as possible. And as you figure out these things and you're filling in the various parts of these equations here and there, you might want to keep a separate list of what exactly is going on. So that way you can keep track. If I need my n, oh, I have it. I need a mean, I have it. Or if I'm dealing with population, I have it here. I have my n. I have my degrees of freedom here. I have my variance. I have my sum of squares in case I need that later. So keep your work organized. Find a spot off to the side. Make these columns. Find the pieces within the equation that you need. Calculate them out. And then it basically becomes a plug and play of variance. And again, this is the mean of all squared deviation scores. And again, thinking back to a mean. Bunch of stuff added up and divided by something else. The same thing. Added up and divided by. The fourth measure of dispersion that we need to talk about is standard deviation. A standard deviation is defined as a rough measure of the average amount by which observations deviate from their mean. So it gives you a rough idea what the average deviation looks like based around the data's own mean. So, like variance, there's a difference in the calculations between a population and a sample. But this is based off of the variance calculation. So there's only a slight difference. So if we're starting with a population, lowercase sigma is the square equals the square root of the sum of squares divided by n. Or in other words, if we were to say the standard deviation, which is what that symbol stands for, right, lowercase sigma, equals the square root of variance. So you do the variance calculation, and once you get through the variance calculation, you simply take the square root of the variance, and that will give you standard deviation. So as far as the calculation goes, really, you've already done all the heavy lifting as far as that goes. So if we were to look again at that original set, that data set we were talking about with variance, and let's just put that information back up here for a second. So we had what was 10, 15, 20, 25, and 30. If we were to put this back up there, and we ran through the whole calculation again, and we did find that, our n equaled 5, and we had a mean equaling 20, and then we said we had the sum of squares, right, which is this top part here, just as a reminder, equaled 250. And then we had a variance equaling 50. You would simply take the square root of the variance to get your standard deviation, which would give us a standard deviation equaling 7.07. Now, if we're talking about the variance of a sample, the same deal. You're just basically going to be taking the square root of your variance. So let's change the color back to black for this. So really, standard deviation equals the square root of variance. So this comes down to basically the same thing. You've already done all the heavy lifting. And if we go back to that data set that we had before, using the same one up in here, which we had already calculated, we would know that our n, since it's a sample, lowercase, n equaling 5. Instead of mu for a mean, we'd represent that with x bar. That's an x. And that would still be 20. And our sum of squares would equal 250. We had degrees of freedom, right? This calculation in here. So the degrees of freedom would equal 4, which gave us a variance equaling 62.5, which gives us a standard deviation, once we take the square root, of 7.91. So as far as the calculation goes, that's standard deviation. In the next video, we'll talk about the deeper meaning of the standard deviation and how it applies as far as our distributions go.